All right, so we're doing lipids. Hmm. Okay, lipids. Most people call them fats, but lipids are a little more complex than just fats. Um, it's mainly divided into two categories: saponifiable, meaning there are esters there, and non-saponifiable, meaning no esters. So don't forget, in a saponifiable ester, which lipids are, um, we end up getting the acid, salt, and the alcohol. There are two main kinds of saponifiable lipids. Waxes, which are very, very simple. That's just a single ester with a really long um, alcohol piece and a really long acid. And I'll show you that in a little while. Triglycerides are a combination of a tri-alcohol plus acids. Complex ones, we're going to mostly focus on these guys here as opposed to these. And then under non-saponifiable, of course, there's steroids and prostaglandins. Okay, so we've got um, simple lipids. Those are just plain old fatty acid and alcohol. However, the triglycerides, we're going to see in a little while, have a more interesting structure. Complex lipids, phospholipids, you've heard a lot in biology talking about membranes. The sphingolipids you probably haven't talked about much at all, but they're not as widely distributed. You've all heard of steroids. You might not have heard of prostaglandins. Prostaglandins are how NSAIDs work. Things like aspirin, Aleve, etc., work, and they start with a fatty acid as a start. Okay, you all heard of fatty acids, I'm sure. They are the building block of almost all lipid-related things except for the non-saponifiable ones, the steroid-based stuff. Basically, we have a really long uh, backbone, and it's usually it depends how long it is, how what the function is. We have short chain fatty acids, medium chain fatty acids, long chain fatty acids, and they're all in different positions within the metabolic strand when you metabolize those for energy. Okay, and they're all stuck on to a polar organic acid head. Okay, so if this is C7 or greater, they tend to be or greater. Let's see. They will not be soluble in water, even though this polar head is extremely polar. It's the most polar of all the substances we've studied so far. Um, frequently, they'll sometimes diagrammatically show it like this. Now, whenever you have a substance like a fatty acid, where you've got a very nonpolar end and a very polar end, we end up, this is in a water environment, a polar solvent, what happens is the nonpolar ends, these guys in the middle here, is red. Tend to clump together, and the polar ends are on the outside, which are touching the water. Like dissolves like. Okay, so the polar ends likes the polar solvent. And the name for those are called micelles. And it's also known as a bubble. Now, if you were to throw these guys into a nonpolar solvent, say like pentane, what would happen? The polar stuff will be in the middle, and the nonpolar tails will be on the outside. This is also called a micelle. In general, fatty acids are straight chains. They range from C4 up to, giant things like 20 C24. They just get really, really large. Now you're going to see in a little while, either today or Monday, how we name these fatty acids. There's actually three ways to name these. There's the omega way to name them. There's the delta way to name them. Then there's the IUPAC way to name them. I'm going to get into all three of those. Now, all of you have heard of cis-trans fats, and trans fats are the bad ones, cis fats are the good ones. However, most biology books always show straight chain fatty acids in a membrane, which is entirely incorrect because the correct fatty acids are the cis ones, which look like this over here. So look like a fish hook. And they never show those. I don't know why. But anyway, those straight chain ones. Excuse me. All right. When we add double bonds to the fatty acids, we end up changing their physical characteristics. They end up being more liquid than solid at room temperature. Like when you buy vegetable oil at the supermarket, it's never a solid. It's always a liquid, unless you're buying palm oil, which is kind of a transition one. Usually it's solid in your hand, it'll actually melt. It's very uh, transition. There's essential and non-essential fatty acids. Essential fatty acids are the ones needed by your body because your body doesn't synthesize them. Okay, these two, I'm sure you've heard of linoleic acid. That's mostly comes from corn. Linolenic acid is one of the most common omega-3 fatty acids. And usually you get that from either fish, and that's cruising fish, like salmon, mackerel, sardines, what else? Tuna, flatfish, like halibut and flounder, sole, don't have much omega-3 fatty acids in them. Linoleic acid is very easy to get. You can get that in any. Notice it has two double bonds. It's weird the way this means it has two of these. Means two sets of those, two double bonds. Okay, you can get those in, and these are the typical omega-6. These are omega-3s. The omega-6s are extremely easy to get. And we usually get too many of them as opposed to the omega-3s. Um, Basically, I just mentioned this here. Okay, so fats and oils. Okay, fats are typically animal sourced, solid at room temperature, and mostly saturated fats. Oils, mainly plant and fish, liquids at room temperature, more unsaturated fatty acids than fats have. Okay, so this is what a triglyceride looks like. The tri part comes from there are three, this is a three carbon backbone with three hydroxyl groups. So it's a tri alcohol. Each alcohol can form an ester with an acid. In this case, we're looking at fatty acids. So, and these can be all the same fatty acids or all different fatty acids. It's usually different ones, and depending on whether they're saturated or unsaturated, will depend upon the physical characteristics of the fat. Okay. Um, let's see. This is basically what I just said. Here's what the alcohol looks like. Although I usually don't draw it like this. I usually draw it like this. And that's really what it looks like as opposed to the straight chain. Um, and this is just a variety of fatty acids. So when you saponify an ester, remember saponification requires an alkaline, strong alkaline or base environment. So this is what we did a couple weeks ago when we made soap. So we had the fats in oil. We put in lye. This is what happened. We ended up with two main components left over. Theoretically, we used up all the lye, and we ended up with the sodium salt of each of the fatty acids and glycerol left over. Now, this reaction goes fast in the beginning and then very slow at the end. So that's why I'm telling you not to take home your soap till the end of the semester, or if you do take it home before the end of the semester, don't use it till the end of the semester. And we can make triglycerides doing the opposite process. So we have the glycerol, which forms as the alcohol. And here are the three acids. Now these happen to be stearic acid, which is a meat-based fatty acid. It's 18 carbons long, totally saturated. So this is what you end up with. Now this only happens in a test tube. In nature, you never get three identical fatty acids. When you do get three identical fatty acids, you can name this as glycerol like trioleate, tristearate, whatever. Normally, though, you don't get three identical, so you don't usually name them that way. You can buy them that way because they're made in a test tube, but if you get them out of nature, like slaughtered from an animal, you don't get three identical ones. Okay, the enzyme for taking apart a fat is called lipase. And that usually happens in the small intestine. So here we have a very, typical triglyceride, TG, and here are the esters. And we hydrolyze that. That means we're adding water, acidic environment. We end up with acids and alcohols. Now, in this case, the alcohol is on the same 3-carbon backbone. And then we get the individual acids that were on the triglyceride as protonated acids. In an acidic environment. When we saponify, we end up with the acid salt, which we're doing right here. So here's the alcohol. These are the acids. And remember, these are called soap. Also, they're called a emulsifier and also called a surfactant. And in the red are the polar parts. In the black are the nonpolar parts. So for a soap, emulsifier, or surfactant, you have to have a polar and a nonpolar part. Okay, so it depends on what you start with for the base. Will give you a slightly different soap. If you start with sodium hydroxide, you end up with a hard soap, like we did in the lab. And if you start with potassium hydroxide, we end up with things like liquidy soaps, like hand soap and dish soap. So this would be KOH, the potassium salt. Sodium salt would be sodium hydroxide. Now, when the pioneers were coming across the plains, like in the Oregon Trail, etc., they always had animals with them that they would slaughter along the way, and then they would keep the fat and they would make soap out of the fat, and among other things. Now, to make soap, we need sodium hydroxide or potassium hydroxide. A way to do that would take the wood ashes. So I always had fires. They take the wood ashes and they would extract with water out the sodium hydroxide or potassium hydroxide. All you do is you just shake the ashes in water, and what happens is the sodium hydroxide is leached out of the ashes by the water. So now we have sodium hydroxide and triglycerides from the fat. Hence, we can cook those together and make soap. Now, there is a process called hydrogenation, which we've gone over in Unit 1. That's where you take hydrogen gas plus a catalyst, and we saturate the double bond with hydrogens. Now, what they do is they do something called partial hydrogenation, and that's taking vegetable oil, like this down here, and doing a partial hydrogenation. That means we get some of the double bonds reacting, but not all of them. The problem is, during that process, the cis These are cis now over here, goes to trans, because trans are more stable than cis. So Crisco Company used to do this all the time so that you can get um, and I see on cooking shows, I watch a lot of cooking shows, and some of the people still use um, the old Crisco. The new Crisco, however, is done a totally different way, and it's totally safe from trans fats because they were about to go out of business. And if they continued on the track of making um, um, what would you call Crisco? I mean, it mimics lard basically to cook with. I was raised on Crisco. My mother used to cook a lot. She used to bake a lot, but she used Crisco. She never used lard. She thought it was unsafe, but good old hindsight. Okay, so there's three main reactions for triglycerides. One is hydrogenation, which we just talked about, and that only works on unsaturated. It only works on unsaturated fats because the unsaturated fats are the ones with the double bonds, and this is a addition reaction for alkenes. Okay, in an acidic and aqueous environment, the ester will come apart to its alcohols and acids. In a basic environment, they come apart to the alcohol and the fatty acid salts. So those are the three main reactions. The main one, though, is on the saturation or hydrogenation, because it only works on if you have a double bond present. No double bonds present, then nothing happens. Okay, so you all are familiar with a wax. Wax things, all of you have seen candles, which are made out of wax, beeswax, which bees make, etc. These are the simplest lipids. They're basically a long fatty acid chain on the acidic side. On the alcohol side is a really long alcohol. Frequently, a test question is what is a wax? And give a simple example. Well, this could be C16, C18, C20. It really doesn't matter. On the acid side, on the alcohol side, same thing. It could be C20, C30. You know, it's a big variety. All of them are solid at room temperature. Now, interestingly, these are extremely stable, so they're not easily taken apart. Okay, a phospholipid, you probably all heard of a phospholipid from biology classes in terms of membranes. The membrane is made up of a phospholipid. Um, it's really a phosphoglyceride because it's made from glycerol. Now, basically, you've got the alcohol part is the glycerol. You have the two acids. Then you've got a, another acid. That phosphoric acid is a triprotic acid, meaning it looks like this. So basically what happens here is it forms two esters. And the fatty acids above it form one ester piece. Okay, and then nothing happens to the third one. So this forms an ester on this end, and that attaches the glycerol. The ester on this end attaches to something else. Frequently, an amino alcohol, which is choline. Choline is a very common neurotransmitter. And this whole thing is called lecithin. And lecithin is a very common emulsifier used in cooking. It's used a lot in building membranes. It's very ubiquitous. Okay, so let's look at the way these are all put together. Okay, so we have a standard ester. Those are the esters. And we have two fatty acids, R1 and R prime. R plain R is different than R prime. That's all that means. Could be the same though, but usually they're not. And here are the dual esters I was just talking about with the phosphoric acid. So this is one ester over here. This attaches the phosphor esters to the backbone. And then this one here attaches to some kind of another molecule. Now, it's going to have an amino group, which is unit 4. We talked about that. An amino group is NH2 or an alcohol group. Either one of those can attach to that phosphate acid there. Okay, so lecithins contain choline. So I have a hard time pronouncing this. Sulfolins contain something else, like one of these guys down here. And this happens to be choline here. No, it's already, it says it there. And these are two different ones. Basically, here's the alcohol part. Here's the amine. Alcohol, amine. And same thing over here, alcohol, amine. So this is officially lecithin. You have to know this or have it on your card, one of the two. And again, if there's an alcohol present on the additions here, it forms an ester. If you're adding to the NH2 amine side, you're going to form something called an amide with NH2. And think of the NH2 acting just like an alcohol. It's very similar to an alcohol. So instead of esters in unit 4, we're forming amides. Same chemistry though. It's a little different, but same chemistry basically. All right, cephalin. We've got a different one here. Again, we've got an ester here because we're using the alcohol side of that. Dual ester up from the phosphoric acid here. And then there are other versions of these. You can have a glycolipid, which contains a carbohydrate unit. Usually it's glucose or galactose. Um, and you need to be aware of these, but you're not going to be responsible for the structure of these. Now, does this look familiar from your test? So this is a non-reducing sugar because it's an acetal and not a hemiacetal right there. These are anomeric hydrogen carbon with a hydrogen attached. Okay. Again, these can get quite complex. All right, steroids. Steroids are based on this unit here. We've got 3 6-sided and 1 5-sided. And they've got to look like this. The most common steroid is cholesterol. Um, Now, cholesterol has alcohols on it. Hence the name cholesterol. Um, but it's got a lot of non-polar groups to it. So it tends to be insoluble in water or blood. And that's one of the problems with it is we need cholesterol as a building block for other molecules. I'm about to sneeze. Excuse me. Um, okay, and there's a whole bunch of steroids in use today medicinally. Um, like I was saying, it's a precursor to other steroids. And frequently people will take a statin drug to lower the synthesis of cholesterol in your liver. Hence, I'm on a statin right now. My cholesterol used to be in the mid 200s. Now it's usually about 120. So the statins really are quite good at lowering your cholesterol. Now, what's interesting, there is a uh, steroid that has enough polar areas in it that overcome the non-polar ones. So this is a emulsifier, and it's this particular one is called bile, and it's stored in the gallbladder, produced in the liver, and what it does is it acts as an emulsifier to break up triglycerides so that the enzyme lipase can work more effectively on it. Okay, prostaglandins uh, are really important. They're the basis of the NSAIDs, the non-steroidal anti-inflammatory drugs. So the important thing in this, you have to start with arachidonic acid. So that has to be in your diet. Now that is a C20 omega-6 fatty acid. And there are 2 enzymes that work on this, COX-1 and COX-2. COX stands for cyclooxidase. Now what happens is these 2 enzymes work on arachidonic acid and produce 2 groups of prostaglandins. One is bad and one is good, but it's usually produced 50-50. So that's why they say if you have an ulcer in your stomach, don't take aspirin because it's clots blood inhibitor, meaning your ulcers will bleed. Um, the one that relieves pain and is an anti-inflammatory is the one that's produced from the COX-1 enzyme, and that's called PGE2 versus PGF2 alpha. This is bad. And I've talked to a lot of pharmacists about this, and what they're working on now is an enzyme that will inhibit COX-2, but not COX-1. So by inhibiting COX-2, you produce less of the bad prostaglandins, and COX-1 produces the good prostaglandins. But it's hard to do, and they're expensive right now. And they're pretty similar in shape. They're basically ketone versus an alcohol. Only difference, really. All right. So structures to know. Fatty acids and general structures. These are the fatty acids. And on Monday, I'm going to go through and talk about this naming. Okay, so this is the delta naming. This is the IUPAC naming. And this is the omega naming. And this would be common name. Docosah is C22. Hex-enoic, it means 6 double bonds. And these are going to be all cis. So it's cis, 6 cis's. Anyway, I'm going to go into detail on how to name those. Okay. I want you to know what a wax is, a triglyceride, and a phosphoglyceride, or a phospholipid. I want you to know lecithin. I want you to know the general structure of the steroid ring. And that's it for today. I'm going to have lots of review next week.
I'm glad because those fatty acids look kind of crazy, not gonna lie.
These guys,
Yeah.
Do we have to pretty much not memorize them, but have a general memorization of what they're supposed to look like the same thing between like when we did carbs of like fructose and maltose and sucrose and things like that?
yeah, yeah. And these would be good to have on your index card. But the naming, the thing about these, biochemists use and nutritionists use, let me back up. Nutritionists use the omega series for naming fats, omega 3s, omega 6s, omega 9s. Biochemists don't. They use the delta way to name things. And then the chemists use the IUPAC way of naming them, like this Icosa 5, 8, 11, 14 tetraenoic acid. I mean, that's the IUPAC way to name it. So that's the problem with fatty acids. They've been around a long time. There's a lot of common names for them. So anyway, so I've got a long, not a long, a very detailed explanation on how those are worked. But I want to do it as a separate day because it's tedious. So yeah, similar to the way we did the carbs. And the lipids aren't hard. They're just like with the carbs, the reactions aren't too bad. It's the structures that are a pain. Okay. I'm going to have some worksheets for you too. I just was checking and the status of worksheets, and there's one there already. That's a multiple choice one, but I'm going to do some fill-in ones, similar to what we did before.
That would be greatly appreciated.
Your worksheets, your book has got a lot of good examples, but the problem is you don't have very many of them. And they're real wordy too. Um, I like to have worksheets where it's just chemistry. Because once you get the chemistry down, then you can throw in all the wordiness and all that stuff. But right out of the chute, the wordy problems tend to be really confusing for students. So, okay, I guess I won't see you till Monday. And I guess we're supposed to get some rain on Saturday. The only reason you should be in lab today is if you have to discuss your project with me. If you don't have, if you've already turned in your project subject, you're good to go. And I'm not going to be in lab because last time I did this class, no one came to lab. Everyone just submitted their subjects. So I'm not going to drive all the way down there for no one. So if you want to discuss it, I'll be more than happy to do it over a private Zoom or over the phone or text. And that works just as well. Okay, anything else?
Just to check the pre-lab for the aspirin lab is for Monday lab, correct?
Correct.
Okay.
You guys will like the aspirin lab. Um, they usually like the aspirin lab and the soap labs are the two labs they really like most of the time. Again, you're going to be using some sophisticated labware. And what's really cool about the aspirin lab is you're actually going to make aspirin. And we're starting from salicylic acid, which is white powder. White powders range from everything from heroin to to sugar. And then so when you make your aspirin white powder, then we're going to prove it's really white powder by running it through an instrument called an infrared spectrophotometer. And we're doing a little bit of chemistry. We're going to do a titration against it as well to prove you have aspirin. So the aspirin lab is a 2-week lab.
Do we get to keep it afterwards?
Sure.
A lot of people don't know, but you can actually break down aspirin and put it inside your flowers when you in your flower vases because it actually helps your flowers stay longer.
These are cut flowers.
Yes, you can. I've only done them in cut flowers. I've never done them in like a potted plant, but they work well on cut flowers. I use my old aspirin for it all the time.
Oh, well, this would be a good use for the aspirin you're making in the lab.
Exactly why I want to keep it.
You can go around and collect everyone's actually doing.
Yes, I will if they'll let me have it.
You sound better.
Oh yeah, and I also figured out why my computer and my phone kept blocking my mic, but I figured out eventually. But I do sound better. My laryngitis went away finally.
Yeah, that was a major outage on Monday, man. The they were worried it was a cyber attack. I don't know if they've ruled that totally out yet or not, but initially
Oh, for the Canvas Amazon thing.
it wasn't just Canvas though. Yes, it was Amazon hosts a lot of business, big business, in their data centers. So when their data centers go down, everything hosted by them gets messed up as well. Canvas being one of them. But it was many, not just Canvas, that weren't working right. And
That's
then when it came on, it wasn't 100%. It was partial only.
well, that's not good.
Another thing that's very vulnerable right now is our power grid.
Mm,
Our power grid is totally controlled electronically, and it's not particularly well protected, which is crazy to me. Really crazy. The amount of money spent on private industry's protection versus our government's protection, like on our power grid. Of all things to not be super protected on, is the power grid. Can you imagine being without power for 6 months?
no thanks.
Yeah, raise your
If I
hand.
deployed and I had power, I pretty sure people can't survive without it.
Yeah, not in
Oh,
this day and age.
No.
yeah. Imagine no refrigeration. I mean, just on and on and on. Heat and cooling. Yeah, we can get by with that, depending on where you live. But man, refrigerator. Can you imagine not having your refrigerator work?
No thanks. I already did that twice. I'm good.
Yeah. Or your gasoline pump that doesn't work. So, all right. Um, are there any other questions? I think we're in good shape.
The lab report, number 3, this was the lecture we were waiting on to complete it, right?
Yeah.
So we can
Yes.
submit it now. Okay.
Yeah. You should after you understand today's lecture and Monday's lecture, yeah, then go ahead and answer your questions. They're basically going to be ester questions, sterification questions. But you should be in good shape to answer those questions now.
And then I also had a question about like my topic, if you have time really quick just to
Sure.
go over. I had 2 ideas. I'm not sure which one would be better. One of them was I wanted to relate it to forensic science because that's my major. One of the ones I was looking at was the emerging practice of using the study of lipids to process latent fingerprints, specifically like the oxidation process, like lipid degradation to determine like the age of the print. This is like a still like developmental thing in forensic science, so I'm not sure if this would be a good topic. Um, Another topic I had was the forensic tests for alcohol-based solvent like acetone and isopropyl as an accelerant to prove that a fire is foul play, like due to arson. Do you think the second one might be better?
The first one sounds more interesting, but I think
Okay.
it'd be a little more difficult to do.
Yeah, I was gonna say.
Um, yeah, either one. If you do the first one, come up with some real simple examples instead of some of the esoteric ones. Um, if you do the second one, you should be able to come up with some, pretty straightforward chemistry.
Okay, thank you.
Okay, anything else, you guys? Okay. All right. Well, you guys have a good weekend. Unfortunately, I haven't seen you, so I have all your tests, as you know, graded, already scored. Um, and I'm going to do the same as I did the last time. You can correct your errors for half credit for people that got C and below.
Cool. Well, have a good weekend as well. I'll see you later.
Thanks,
Connor, you're
Professor.
taking, Connor, you're taking off next week, is it?
I'm taking off on um Saturday,
Saturday. Okay.
so I'll be
Since
gone next week and the week after.
yeah, since Connor is my lab partner, can I just give him all the information that I do in lab for our wet lab stuff?
Yeah, you can do that.
Okay, sweet.
Nice. Thanks, Gina.
Yeah, of course, man. Do you have WhatsApp?
No, but I could get it.
Yeah, download WhatsApp because you can use it internationally for free and it links your phone number. And then I can send you all that information. So if there's things due, you have all the information before it needs to be done. I'll let you
Sweet.
know.
All right. Thanks.
No problem.
Catch you later.
Bye.
Sorry, Professor, I had one more question.
Yeah.
I just wanted to clarify something on my chapter one test correction. Would it be easier to email you the question I'm talking about or text it?
It was a question on your first test.
Yeah, it's on the reactions part, so like the drawing, I don't know if it'd be easier to like email you a picture or text you. Or I could wait till Monday maybe to come in and have you explain it to me. I'm not sure, whatever works better for you.
Well, in person it'd be best, but if you want an answer before then, it would be best to take a picture of it and then email it to me.
Okay, I'll probably do that.
Yeah.
Thank you.
Can do it.
Bye-bye.
Okay. Bye-bye. See you later.